guys, I hope you guys are having a wonderful day, and we are moving on to our second video in our first unit. So last time we talked about uncertainty and measurements and how to propagate uncertainty. So we're just going to do a quick short video reviewing how we should graph our data. So because once we have our measurements, it's important to graph them properly. So this might be less than 15 minutes. We'll see how quickly I can get through it. Okay. So when we graph data, the independent variable is going to be on the x-axis, whereas the dependent variable, what we are measuring, is going to be on the y-axis. So in this example here, I know there's a lot on the screen, but I will take it step by step. This graph shows the results of measuring the mass of copper after changing the volume of copper. So the slope of this graph would give us density because density is mass over volume. So you can see the different volumes here and the associating mass measurements. And you can see that we put a scatter plot as our graph here because, 99% of the time the graphs will be a scatter plot. And that's because we want to be able to predict relationships between our variables. So we want to fit that data with a trend line in order to interpolate, aka we are going to predict what the value should be between the data points, or we can extrapolate the data, which means we can predict what the value would be outside of our measured data range here. And we can do that because we can fit the data with a trend line, and there will be an equation here that represents our trend line. In this case, it is linear, so we have it in the form y equals mx plus b. And then we have different values that can tell us about the fit of our trend line to our data. And those two values are going to be the correlation coefficient, which is represented by this lowercase r, which tells us the magnitude and direction of the relationship between the variables. So last year we only talked about the r squared value. I want to make it clear that there are two different values we're talking about here. The correlation coefficient is lowercase r, whereas r squared is called the coefficient of determination, and I will tell you about the differences between those in a second. Okay, so r tells us if the relationship is positive or negative. So r can vary anywhere from -1 to 1, and if it is closer to either of those extremes, it tells you that the relationship between the independent and dependent variables are stronger. And if you had an r value around 0, that means there is no significant relationship between the independent and dependent variable. The r squared value now, this tells you the amount of variance in the dependent variable that is explained by the independent variable. So r squared really tells you about the spread of your data. So it is actually a percentage. You get it in decimal form, but you say, okay, for this example, r squared is 0.98. That means 98% of the variation in the mass of copper can be explained by the volume of copper. So therefore, because it's really close to 1, the spread of our data is minimal. So there's minimal variation in that dependent variable that cannot be explained by the independent variable. And the r squared value is different from r because it only goes from 0 to 1. 0 meaning the variation in the dependent variable cannot really be explained at all by the independent variable, and an r squared of 1 means all of the variation in the dependent variable is perfectly explained by the independent variable. And hopefully that makes sense, but if not, let me know. Okay, moving on. Look at this cool thing that I have now. This is an interactive whiteboard where you can actually click on this and it'll send you to a Canva link where you can post your thoughts on the discussion prompt, which is why should you never just connect the dots of data points in a scatter plot? And you can actually build off what other people say. You can add images. It's really cool. So I do want you guys to please participate in this. Okay, so let's look at some more examples of graphs and interpreting what the data means. So because our r value, our correlation coefficient, can be anywhere from -1 to 1, we can have positive correlations or negative correlation. So a positive correlation means as the independent variable increases, there's also an increase in the dependent variable. Now notice it does not necessarily have to be linear. Okay, I know there's a lot of things online if you Google this telling you that when you're talking about R squared and R values, it's only representing linear relationships between data. That's not necessarily true. I did a lot of research on this, and ask me in class if you want me to explain it further. But there can be other types of trend lines that can be represented by R squared values, and those include like polynomial and logarithmic, which is really the only other two types of trend lines that we're going to be discussing in this class. So I just want to let you know it is perfectly acceptable to talk about an R squared value in terms of non-linear trend lines. Okay, so now that that's out of the way, this example is the volume of hydrogen gas produced whenever you treat a metal with hydrochloric acid, so it lets off hydrogen gas. So this relationship is that as the volume of hydrochloric acid increases, so does the volume of gas produced. But it does so in a non-linear fashion. This is more of a polynomial fit because the level of hydrogen gas is eventually going to level off. So in this case, the R value is 0.96, very close to +1. So that means that the relationship is positive and the relationship is very strong. So there, as the independent variable goes up, the dependent variable goes up as well. And the R squared value, the coefficient of determination, is 0.99, which means 99% of the variation in the dependent variable is explained by the independent variable. You can look here at another example. This one is moderate correlation here. So this is showing the product yield versus reaction time. So as you increase the time of a reaction, you're measuring the amount of product you are obtaining. And you can see here that the R value is a bit lower. It's 0.79, and the resulting R squared value, which literally is if you just square the R value, you get R squared, it's 0.64. So that means 64% of the variation of the product yield is explained by the reaction time. However, this relationship is more moderate, and that's because it could be a couple of reasons. Maybe there are some uncontrolled factors in your experimental design that you have not accounted for that is affecting your product yield. Or it could be there is some type of error in your experiment that you are not accounting for that is contributing to this variation. But if you have something that is a more moderate correlation, there are some things that you need to be talking about in your evaluation as to what explains this variability in your data. Okay, you can also have strong negative correlations. So this example is talking about reaction time and the concentration of a reactant. So as the reaction proceeds, the concentration of what you're starting with is going to go down. That makes sense. This is also a nonlinear correlation. You can see by the trend line here, it's more of a polynomial. Your R value is still rather strong. It's negative 0.89. So the negative indicates it is a negative relationship, and it is a strong relationship, meaning that the concentration and time variables are strongly related to each other. And 85% of the variation in your concentration of your reactant is explained by the reaction time. So strong relationship. Let's look at a weak correlation. Okay, a weak correlation, you can see this R value is negative 0.46, so rather low. It's pretty more closer to 0 than it is to -1. And you can see that the R squared value is only 0.22. So only 22% of the variance in the dependent variable is explained by the independent variable. So that means 78% of that spread of your data is explained by other factors other than your independent variable. So in this case, we're looking at absorbance versus pH. So the pH of your solution is really talking about the level of acidity or basicity. So you can see as it gets more basic, the absorbance values, which you're shining a light through your sample and you're just looking at how much your sample absorbs light. The absorbance goes down, but it's very weakly correlated. So there's probably a lot of other factors in this scenario that you have not controlled for that is affecting the absorbance of your solution. Okay. And then let's look at a moderate linear negative correlation here. You can see the relationship between boiling point and altitude above sea level. So as you get higher above sea level, the boiling point actually goes down because there's less pressure exerted on the solution. But you can see that R is rather a moderate value, it's negative 0.78, so that means the r squared value is 0.61. So, sorry, let's just say 61. 61% of the variance in the boiling point is explained by the altitude above sea level. Maybe there's some other factors that you did not account for here, or there's some type of random error in your measurements that means 40% of the variation in your data is not explained by solely the level above sea level. Maybe you didn't account for things like temperature, which can significantly affect the boiling point of your solution. I mean external temperature. And then let's look at something with no correlation. Okay, no correlation. There's such a large amount of variance in the dependent variable with respect to the independent variable that no significant relationship exists. One example, if you're trying to measure the concentration of a salt solution with respect to the mass of your beaker, the mass of the beaker that you're making your solution in should have no impact at all on the concentration of your solution. And if there is, maybe there's something wrong with how you measured this data. But the R value is only 0.1, meaning only 6% of the variation in your concentration is affected by the mass of the beaker, so nothing significant at all, which does make sense. So a little note about correlation coefficients. The boundaries between R values that indicate, perfect correlation, strong, moderate, or weak, they're very subjective. I've seen lots of different journal articles tell me, like they'll say a 0.6 R value is still a strong correlation. My rule of thumb is if you have anything above 0.8 or anything below negative 0.8, that is a strong correlation. Anything between 0.6 and 0.8 or between -6 and -0.8 is about a moderate correlation. Anything below that up to like -0.2 or +0.2 is more weak correlation. And then below 0.2 or from -0.2 to 0, that's like not really a significant correlation at all. But this is subjective. It's just my general rule of thumb. You might see differences in the interpretation of R values depending on the source that you use. And remember, R squared values, the coefficient of determination, closer to 0, indicate that other uncontrolled variables or error is contributing to the variation of the dependent variable. All right, so this is a new thing I added this year. You can basically click on the answer you think and the correct answer will show up, or if you get it wrong, an explanation of why it is wrong is going to show up. But how is a correlation coefficient different from the coefficient of determination? Go ahead and click the answer you think. Okay. And here's another group discussion. If you did an experiment and got a weak correlation, would you consider your experiment a failure? And explain your reasoning. And then last, a little note about data. Correlation does not equal causation. Just because your dependent and independent variable are strongly correlated does not mean that one is causing the other. So be careful about using the word cause in your conclusion of your lab reports. You can say that they are correlated with each other, or you can say that your dependent variable increases proportionally with your independent variable, but not that one causes the other. Remember, there's no absolute truth in science, and data does not prove anything. You either have evidence that supports your hypothesis or does not support your hypothesis. A note about this correlation versus causation. This is a graph showing shark attacks and ice cream sales over the months of the year, and you can see that these graphs line up pretty well. So from this, you cannot say that ice cream sales cause shark attacks. However, ice cream sales and shark attacks are correlated with each other because most of the time people are out swimming in the summer months and they're eating ice cream when it's hot outside. So of course those are going to peak around the same time. So that's just a little example to say you can't say your dependent variable is caused by your independent variable. You can say they're correlated with each other. And also, whenever you're designing these experiments, make sure you are controlling any other variables as much as possible. You will get much higher marks on your IA if you have a long list of variables that you have controlled in your experimental design. All right, guys, that's it. I managed to keep it on time. So I will see you tomorrow in class, and I hope you have a great rest of your weekend. Bye.